Okay, so we're going to have a look at another question from electromagnetism. We're told an electron is moving through a horizontal uniform electric field that points left and has a magnitude of 1.5 kilovolts per meter. At time is 0, we're told the electron's velocity is 3 kilometers a second and the velocity is registered at a 45-degree angle to the field. Find the velocity in x, velocity in y, and total velocity, as well as the kinetic energy of the electron at the following times: 0, 1, 2, 3, 4, and 5. We've been asked to sketch kinetic energy versus time. We've also been asked to calculate the work done over the 5-second period. Okay, so we need to set up our acceleration, velocity, position formulas. So we'll draw a diagram. We're told the field points left. So the field is going left. That means we have positive plates on this side. This is positive. And then we have a negative plate on this side. This is negative. This makes the field point to the left. This is what we've got. Now the electron moves through and its initial velocity is 3 kilometers a second at a 45-degree angle. So it's sort of here in the field. It's going this way so that this angle is 45 degrees. And its initial velocity initial, is 3 kilometers per second. Now, we can work out the velocity initial in x and y straight away if we want. So we can say if this is 3, we'll convert this to meters per second because that's going to make more sense. So this is 3,000 meters per second. It has a velocity in x and a velocity in y. Velocity in x, velocity in y. We're going to choose our standard Cartesian coordinates. You can pick other coordinates, but Cartesian coordinates fine. So we have a negative velocity in y. We have a negative velocity in x, and we could swap this all around and make these positives. I've just picked this one, so they're going to be negatives. It doesn't matter. It doesn't make any difference. So this is 45. So these will actually be equal because this is an isosceles triangle. So we just need to calculate one of them. V of x is equal to V of y. So we are going to get, let's use sine. We've got sine of 45 is equal to opposite of hypotenuse. That's V of y over 3,000. So this tells us V of y, the initial velocity in y, which is equal to V of x, the initial velocity in x, is 3,000 times sine of 45. So 3,000, we'll just numerically approximate this straight away. 3,000 times sine of 45 is about 2.12 times 10 to the 3. So this is 2.12 times 10 to the 3. Now these are both going to be negative, but the magnitude of them is 3,000. So the magnitude of these velocities is 2.12 times 10 to the 3. Now let's draw a little diagram for accelerations in x and accelerations in y, and let's start calculating these. So there's no gravitational acceleration here. We're assuming no gravity, so no g. No g. The only acceleration we care about is the acceleration from the field. Now, as we've done many times at this point, we can calculate the acceleration from the field. We need to think as to whether it points in x or y. This is an electron, so it has negative charge. And that means it wants to go towards the positive. Right? The negative wants to go towards the positive in this case. And in the way that I've set up the question, that means that pretty much it's going to spin around this way. And again, it depended how we set up the question, right? So if we wanted to make this question a little bit easier, and we could do this, we could get rid of the vector from up here. We might do this. It doesn't really matter. It's an acceptable answer of the question either way. We may say that it launches like this, where this is 45 and this is 3. So this will make the accelerations both positive. It'll make the acceleration positive, sorry, but it'll make the initial velocities both positive as well. So this is actually nicer. Relatively small change, but pretty much solving the same thing. It's different views on what the question is asking. So we can pick either. We'll pick this one because it's a little nicer. So this is still going to be the magnitude of the velocities. Now they will be positive because we've picked positive x, positive y. So acceleration in x. This is an electron. It has negative charge. It's going to go towards the positives. So the acceleration is only in x. There's no acceleration in y. So acceleration in y is 0. Acceleration in x is going to be equal to the charge times the field divided by the mass. The charge on an electron, so charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. The field in the question we've been told has a magnitude of 1.5 kilovolts per meter. This is 1,500 volts per meter. So we get minus 1.6 times 10 to the minus 19 times 1500 divided by the mass of the electron, which we know to be 9 times 10 to the minus 31. 9 times 10 to the minus 31. So this is really crammed in here, but that's fine. It's going to give us the number we want, so that's okay. This will be positive, remember, so we're just going to ignore this negative. We only care about the magnitude. 1.6 times 10 to the minus 19 multiplied by 1500 divided by 9 times 10 to the minus 31. I get 2.67 times 10 to the 14. 7 times 10 to the 14. So this is just phenomenal acceleration in x in terms of meter per second squared, and acceleration in y is 0. So now we have our accelerations. We need to find the formulas for velocity and formulas for position. Then once we've got the formulas for velocity, we'll find them at t is 0, 1, 2, 3, 4, 5. For the Vx, Vy and velocity, we'll find the kinetic energies as well based on those velocities. Sketch kinetic energy versus time, and then we can do the work. Notice we don't need position in this case. Right? We normally calculate accelerations, velocities, positions. We're doing a lot of work with velocities here, so we're going to save ourselves the time of day, and we're not going to do the positions. So we're going to do the velocities. We get velocity in x is this number times time, 2.67 times 10 to the 14 times time, and then the acceleration of velocity in y, velocity in y. We have to add our initial velocities to these, of course. So velocity in x is this, plus the initial velocity in x, which we said was 2.12 times 10 to the 3. 2.12 times 10 to the 3. And then the velocity in y is just 2.12 times 10 to the 3. Now, before we do anything else here, we're just going to take a moment to acknowledge how stupid some of these numbers are. Right, the 2.6 times 10 to the 14, this acceleration is just going to, at any time above incredibly tiny values of time, this is going to massively overwhelm the initial velocity. Right, so we've been given a question here where we're working with unfathomably large numbers. And this is very odd. You can't picture this, right? You can't imagine this. You just have to trust the mathematics. If you're doing the mathematics right, the numbers will come out right. They'll look weird, they'll have crazy high powers, but they'll come out right if you do the maths right. Right? A lot of higher end physics is just about maths. There is no physical analogs. You just can't see what things look like. You just have to be good at doing math. And if you're good at doing math, then you'll get answers. If you're not, you won't. So now let's start evaluating these velocities. We may as well draw a little table of values. So we will have velocity in x, we'll have velocity in y, we'll have total velocity, and then this will be the time. So I'll do it this way. You could do it the other way, doesn't really matter. I'm not going to write all these formulas down, I'm just going to calculate them as I'm going through, because this is a type of very long question where there's a lot to do. So times, we need 0, 1, 2, 3, 4, and we've been asked for 5 as well. We can make this go to the edge of the page. Like so. So now, velocities in x. Well, when time is 0, it's 2.12 times 10 to the 3. velocity y when time is 0 is 2.12 times 10 to the 3. And we know from the question that the overall velocity at the start was 3 kilometers a second. So we will do this not in kilometers, but we'll do these all in meters a second. So this is 3 times 10 to the 3. Now at 1, we're going to get 2.67 times 10 to the 14 times 1. The 2.12 times 10 to the 3 doesn't matter anymore. Right? It's just so small. When we're rounding this times 1, it's just going to go away. So this is just going to be 2.67 times 10 to the 14. Y will stay the same, 2.12 times 10 to the 3. And in fact, y will stay the same the whole time. 2.12 times 10 to the 3, 2.12 times 10 to the 3, 2.12 times 10 to the 3, 2.12 times 10 to the 3. Now when we find the next x, it's just going to be double this, because now time is 2, so we get 2.67 times 10 to the 14, and then we're going to multiply this by 2. This is 5.34 times 10 to the 14. 5.34 times 10 to the 14, and then 2, 7, that whole thing times 3, so this will be 8.01 times 10 to the 14. And then if we do it by 4, this will be 1.068 times 10 to the 15. And then if we do it by 5, we'll get 1.335 times 10 to the 15. Now the interesting thing here is the velocities, because we're rounding them to say 3 or 4 significant figures, they're just going to be the velocities in x. These velocities are so massive that they are absolutely going to overwhelm. When you could do the square root of sum of squares to find the velocities, you don't need to. This will just be 2.67 times 10 to the 14. This will be 5.34 times 10 to the 14. This will be 8.01 times 10 to the 14. This will be 1.068 times 10 to the 15. This will be 1.335 times 10 to the 15. These are just going to be exactly the same because this is so slow compared to the velocities in x. So this is all of the velocities. Now we can find the kinetic energies at these times as well. The mass of an electron we know is about 9 times 10 to the minus 31. 9 times 10 to the minus 31. And we know that kinetic energy is a half times mass times velocity squared. So we can just start evaluating the kinetic energy at all the given velocities, all of these values. So we'll do a little table for this again. We'll say time, and then we'll have kinetic energy. So time here, kinetic energy here. We'll have 0, 1, 2, 3, 4, and 5. And then you can just put this in your calculator. So we can go half times the mass will be 4.5 times 10 to the minus 31. Need to multiply that by each of the velocities squared. So we start with 4.5 times 10 to the minus 3 multiplied by 3 times 10 to the 3 squared. This is 4.05 times 10 to the 4. And now we need to change the velocity to the next velocity, which is 2.67 times 10 to the 14. So this becomes 3.2 times 10 to the 26. This would be much better to do on a computer, but we can use the calculator to do this. Then it becomes 5.34 times 10 to the 14. This becomes 1.28 times 10 to the 27. Now we have the velocity increasing. This becomes 8.01. So this becomes 2.88 times 10 to the 27. Then we have the velocity increasing again. Becomes 10.68. So this is 5.13 times 10 to the 27. And then we have our final value here. Thank goodness. This is 13.35 times 10 to the 14. So this is 8.02 times 10 to the 27. So pretty much it starts off relatively low, then just gets up to numbers to the power of 27 and pretty much stays there. If we wanted to graph this, this is likely to just look like a sort of logarithm. So the kinetic energy, let's imagine that this is 10. Let's imagine this is 10 to the 28. This is a term slightly larger than the number of 5. It's not necessarily the case that it's asymptotic to this, but this is going to be useful. We start off after 1, and then 2, and then 3, and then 4, and then 5. At 0, we're relatively low. 10 to the 4 is like essentially down at 0. And then we go to 10 to the 26. So this will be maybe, let's say this graph is not to scale. The scale doesn't really matter, but we want to try and give a good impression of the curve. Something here. This is much better on a computer, by the way. Then we get 1.28 times 10 to the 27. That will be like up here. We'll make this point a little higher. And then grows a little more, and a little more, and then a little more. So this number is essentially doubling every time. So it's going to go something like this. Remember, this graph is not to scale. This is not good to do by hand, but it's just going up at such a phenomenal pace. And in fact, if we think about this, if this is 10 to the 28, this half of this will be 1/2 times 10 to the 28. And this will be 5 times 10 to the 27. So let's try and make this as accurate as possible. This is a silly graph to do by hand. 5 times 10 to the 27. So our fourth score is here. We really want to get this curvature right. 5 times 10 to the 27, that is the fourth score. And then 8 is sort of up here. And then we have 2.88 times 10 to the 27. That's much lower. Now that will give us, that's half of 5, so that must drop down to here. Then it will halve again, and then it will just go right down. This is better curvature. This is a much better scale. Sort of just going up like this. It's approximately parabolic in shape. And so this is time. This is the kinetic energy. Something like this. Not necessarily a parabola, but this is the kind of shape that we're after, nevertheless. So this is A. This is the answer to A and the answer to B. Now for question C, we're told calculate the work done over the 5 seconds. So here we are going to shorthand ourselves. We are going to find the magnitude of the work. And essentially this is going to be related to the change in kinetic energy. So we're going to say work is change in kinetic energy. So this means final kinetic energy, which is 8.02 times 10 to the 27 minus initial kinetic energy, which is 4.05 times 10 to the 4. Well, this means that the work is actually just 8.02. 8.02 times 10 to the 27 when rounded to 3 significant figures, 3 sig figs, because this number is so much more massive than the initial number. So this is the work done. So this is one way to approach this kind of question. This is a bit, we're getting to the point where these are a bit silly to do manually. So when I'm doing a video like this, this is very, very tedious to do in terms of manual working. It's much better done on a computer, but you can do these manually, right? And when you learn them, you do them manually so that you can learn about them, then you can learn to think about them, right? So when you're doing these on a computer and you're sort of programming how to get something to produce this, you can think, is that correct? Yes or no? You can sort of look at the graphical output the computer gets you, and you learn to think about that. That's an incredibly long question, lots of sort of trivial, tedious working, but it's a very good example of a type of manual physics calculation.